Okay, good afternoon. I'm sorry to be with you 2 times a day. I hope it won't be that heavy lecture, but as usual, we should have tutorial session in the afternoon. Before I start, just to make sure, can you all see the problems, the tutorial problems, 630, 636, 637, and 638? Can you all see that before we start giving the lecture? Yes? Can you all see the slides or the note here? Sorry, the OneNote. Okay, good. All right. Before I start the lecture, today morning I solved 2 problems on chapter 6 from the tutorial sheet. Anyone has any question on those? Because I just want to make sure that you can go to this team table and get the data from. By the way, this chapter is mainly about this. If you were unable to collect the data from the table or from the appendices, then you would have an issue in solving the rest of the problem. So any question before I start the tutorial session? Any question on the first problems that we did today morning? You all okay? For some reason I'm unable to see. Okay, I can see some of you responded, so it seems you were fine. Let me start the remaining of the problems. So we'd have to start with 630. As you can see here, tutorial 10. I have tutorial 10, 630, and I will start with the first problem. So let's see what we have. Here we have superheated steam. And that superheated steam is at 500 kilopascal at the inlet. First of all, the state has been defined as superheated. The pressure was given as 500 kilopascal, and the temperature also was given as 300 degrees C. So the process, if we would need to draw the PV diagram, it is simply expansion process, and it is asentropically. So I would just write here asentropic. Now keep in mind that it was written asentropic, then I know that delta S is equal to 0, right? And the initial temperature was given, initial pressure was given, so those are the given information, and the final pressure is also given as 50 kilopascal. So those are the given information here, that's 500, and here the temperature is 300 degrees C, okay? All right, so these are the given information. Now in the question, it was simply that they were asking for the final enthalpy. Final enthalpy means H2, all right? Now if we are going to start solving the problem, similar question can be given before if it was ideal gas, and you can still solve it using ideal gas behavior if it is ideal gas. So my advice is that always whenever you are going to start solving a problem, ask yourself, if such a question was given while ideal gas behavior was there, how can I solve? And if it is actual or real, based on real experiments and real data that's not ideal, how can I solve? Very important to ask yourself these questions, because possible questions can be given either on ideal or non-ideal. Is it? At state number 1, since I have 2 properties, the system is supposed to be fully defined, or the state is fully defined, especially that they said already it is superheated. The question before I solve, do they need to tell me that it is superheated at state number 1? I can give the same question without saying it's superheated, but because I have been given T1 and P1, I can simply go to the thermodynamic tables. And from the appendices, I would go for F2. I normally prefer F2 over F1 for a reason. F2 is more comprehensive because it shows, the first 2 columns shows the saturation condition, and then the remaining shows the superheated. Unless you cannot get the information from table F2, then you can go back to table F1. So this is, I personally would prefer to go this direction. So from table F2, at a pressure of at P1, you will notice that the temperature that is given is greater than Tsat, okay? I would here specifically, of course, I cannot wait for you. I'm just explaining how you have to check it. If the temperature is greater than Tsat, then it is superheated. Now here in the question, they already mentioned it is superheated. But make sure that you can read this information from the table. Okay, the question here is how to get the final enthalpy. Now, when I go to the final state, again, I will ask myself, is it fully defined? Can I define the state here or not? I do have only one information, which is P2. And here's the point. Again, I will repeat, having only one property per state or per point is not enough. According to Gibbs phase rule, I have to have at least two properties. So at state number 1, it's fully defined. Any information needed at state number 1, I can get it. Yani if in the question they said how much H1, how much S1, how much U1, you can get it because you do have two properties that fully define the system. But the problem here is that they were asking information about state 2, and at state 2 I only have P2, which is 50 kilopascal, unless I have a relationship between state 1 and state 2, and this is what we mentioned today morning. Today morning when we solved some problem, there was sometimes there are links between state 1 and state 2. Here, what is the link? They already mentioned that between state 1 and state 2, it is asentropic. And because it is asentropic, delta S is equal to 0 means S1 is equal to S2. And this is the information that I will need here. Yes, I don't have other than P2 given, but once I found S1, then I will be able to fully define state number 2. Because of that, what I will do is this. Here, I'm just going to write for you S1 is equal to S2 because it was asentropic. Delta S is equal to 0, and that's why S1 is equal to S2. But what I need, as I said, is to define what is S2. S1. How you will get S1? Okay, you will go to table F2 at T1 and P1. The intersection between the two, you have to read S1. I would just wait a few minutes just to make sure that you really don't have a problem. Can I just wait here and for you, and I need to see in the post at least a few students finding the S for me at a pressure of 500 kilopascal and a temperature of 300 degrees C. If you do have the book in front of you, please let me know how much is the value. Thank you, Ali. Ali got it as 7.4614. How about the rest? Are you getting the same value? I just want to feel comfortable or feel satisfied that you are in the right direction. If you are not, then we would have to give further explanation. Can you check how much is the entropy? Okay, Ali said it is 7.4614. Do you all agree with Ali? If you agree, just write agree, otherwise put your own value. Okay, I'll just wait a bit. Okay, hello? Have you managed to get the value? Okay, good. I got some students who agreed and some who put the same value. So in this case, you are in the right direction. That's wonderful. So according to the steam table, the value is 7.4614. Thank you all. And that as entropy value, it is kilojoule per kilogram Kelvin. Kilojoule per kilogram Kelvin or joule per gram Kelvin. All right, so that's regarding what? Regarding the entropy. And now that state number 2, I have P2 and S2, I should be able to define the state. How can I say the state? When you go to, again, I would go to table F2. Why I will go to table F2? Here I have no option. I have no option other than going to table F2 because the pressure is given. It's not temperature. So it is a pressure-based information. And F2, as we agreed, it is a pressure-based table. So when you go to table F2, okay, with table F2 at a pressure P2, my P2 is how much here? it is, according to the question, it is 50 kilopascal. Okay. When you go to table F2 at 50 kilopascal, you will go horizontally. There are two columns here which shows the liquid, saturation liquid and saturation vapor properties. So what you will need to do, you will need to get S liquid and S vapor property and check S2 is how much compared to those. If it is in between, then it is saturated mixture. If it is less than S liquid, then it is subcooled or compressed. If it is greater than S vapor, then it is superheated. And this is very important information. Okay. Now, for those who has the table in front of them, I hope you can see that S2, it is in between S liquid and S vapor. And because of that fact, then I can simply say that I have saturated mixture at state 2. All right. But the point is, if it is saturated mixture, then the question is, how can I find enthalpy? Remember what they need in the question, they need H2. And I cannot find H2 if it is saturated mixture unless I know the quality. Remember, I will keep what I said this morning. If it is saturated mixture, then I have a full region between liquid and vapor. Unless I know the quality, I won't be able to define the exact state or the exact point. So the question here is how to get the quality. Once I know the quality, I will be able to solve. Now, keep in mind that the quality is defined in a formula which says that M is equal to M liquid plus X MLV. And this is what we said. Now, M can be S, can be U, can be H, or can be specific volume. So this is what M means. Because of that, what I will do, I will substitute here, since I have S2 and I have S liquid and I have S vapor, S liquid and S vapor, I got them from table F2. S2, it was equal to S1, which you agreed with me that it is 7.4614. Then here I can just substitute. Substitute means I will put S liquid. For those who are following the book, you can see that S liquid is 1.0912. The equality is the unknown. MLV means what? Means S vapor minus S liquid, and S vapor is 7.5947 minus S liquid, which is 1.0912. And the property that I have S is the S that you agreed S1 is equal to S2, 7.4614. So this is 7.4614. What I did here, I just applied that equation on the entropy. Why, Doctora, you applied it on the entropy and not in anything else? Because I have the information about the entropy. S2 is equal to S of liquid, and here S of vapor minus S of liquid in order to get the quality. So this is the formula. So with that, you can just solve and get what? Get the X as a quality. I will remind you that this quality means the mass of fraction of vapor in the mixture. So in other words, here, when I get it 0.98, it means I have 98% of the mixture is vapor. The remaining, which is 2%, is only liquid. خلاص? Knowing X means I am done. I am done in terms of defining the states. I do have at state 2 that the pressure is equal to 50 kilopascal. And now that I know that the quality is equal to 0.98, then I have no problem, because at this pressure, at P2, I can get H liquid and H vapor. And Director, why I want H liquid and H vapor? Because in the question they were asking for H2. And H2 is going to be equal to H liquid plus X as a quality, HLV. Same as what I did with the entropy. So if this is the case, H liquid and H vapor can only be found from table or from appendix F, which is table F2 specifically. Okay. And then, Doctora, why you want the table F2? Why it is only saturated mixture? I told you the first two columns of the table shows the saturation condition. So that's why HL and HV are the saturated properties. Okay, the saturated properties. طبعا, if you go to the table and check the values, you can get the H liquid and H vapor. If I'm not mistaken, here according to what I have in front of me, H liquid is equal to 340.4564. plus X the quality, which we put it as 0.98. Now HLV simply means H vapor minus H liquid, which is 2646.9 minus 340.564. Now I want to tell you something. The advantage of table F1 is that this HLV is ready for me, and it's called H evap, or the column that is called evap. But it's not a difficult calculation to do. It's simply the H vapor minus H liquid that you can just subtract. Okay? So with that, I can find the final enthalpy here. You will get it as 2599.6 kilojoule per kilogram, or joule per gram. That we had here, 630. Before I move to the other problem, I hope the question is clear. Okay, before we move further to another question, is the idea clear? Okay, thank you very much, Ali. He was just with me, I think, figuring out the answers. So that's great. So if it is clear, I will move to the other problem. We need to solve as many problems as possible, so I would have to move to 636. Okay, 636, what do we have here? Now, there is something interesting here in that question. What is it? In 636, this is the second question in this session. Keep in mind, we already did 2 questions today morning, so this is the 4th one in order. Okay, so with 636, it combines previous chapters like chapter 2 and chapter 3 with today's lecture, or this chapter. And let's discuss how is this. Here, it has been given that we have 1 kilogram of steam. So I have the mass as 1 kilogram. But it was mentioned it is steam. Look, if it was in chapter 3, it would have been mentioned that maybe it's ideal gas. Here it's a steam. And remember those thermodynamic tables, and I hope I mentioned this before, but if I did not, those thermodynamic tables are only for steam, and steam only. Now, is there other tables that are for other than steam? Yes, there are, but in your book, you do have only the steam table. And that steam is contained in a piston cylinder device. So I do have piston cylinder device. This will just give me an information, a very important information, that I have a closed system, where the pressure is given P1 and the temperature is given as T1. Now, what we have in this question, basically, they were saying if it undergoes mechanically reversible isothermal expansion, yani what I have in this question is if I want to draw the PV diagram, I'm moving from T1 and P1 through reversible isothermal. But this will take me, because of the expansion, because they said reversible isothermal expansion. Because of that expansion process, it took me to P2, which is much lower in terms of pressure than the initial pressure. So that is what's happening. What they are asking for in part A, they are asking for the Q. Now, if such a question has been given in chapter 3, of course, the first thing you would think of, it's a closed system. And because it's a closed system, I have to apply the first law of thermodynamics. For a closed system, I would say Q plus W equal to delta U. Now, if it was ideal gas, I can just substitute, and here piston cylinder device means I cannot ignore W, because it's a piston cylinder device. Definitely there is work, so I have no choice to cancel the work. Okay, and it's reversible isothermal. Now, if it was ideal gas, then I can say delta U is a function of temperature only. I will cancel delta U and I will proceed. But here, it's reversible isothermal, but it's not ideal. It's a steam. Now, the question here would be, they ask for a Q. And it was clear for me, even that if I found delta U from the system and how to get delta U, let me just tell you the idea. Now, at T1 and P1, I can fully define it. Okay, state is defined. Why it's defined? Because I have 2 properties. Yani, if I want to find U1, I can find it from the appendix. It's not a problem. Now, and because it's isothermal, I can simply write here T1. And again, at state 2, it's fully defined because I have 2 properties. Okay, so if this is the case, then again U2 can be calculated. Again, we have no problem. Then delta U can be easily calculated according to what I have. But the question here, how can I get to Q while W is not known? And this, I want to remind you with something that is very important. What is this? Remember that if I want to find the Q for reversible process, it is equal to T delta S. And this brings me to what? It brings me to chapter 5. Now, this information is very useful here because I do have isothermal process and the temperature here is just a constant value, which is 473.15. That's wonderful. So now it's just the idea of how to get S1 and S2. Now we agreed that at state 1 it is fully defined. So S1 I can get it easily. S2 I can also get it easily because I have two properties. So the idea here is just how to get Q reversible. And to get Q reversible, it is simply T delta S. So once you find both S1 and S2, you will have no problem. Now, based on the given information, and you can double check this, at C1 and P1 given, it is actually superheated. And how do I know that it's superheated? Let me just tell you the procedures. What you will do, you will go to table F2. Again, as I told you, I prefer to go to table F2. You can go to table F1 if you like, but make sure that you know the concept. What do I mean by this? A table F2, because it's a pressure-based table, then what I will do, I will go at P1, and then I will see how much my temperature compared to the Tsat, which was written in the table. In the table, it's pressure-based, but under each pressure there is a bracket where this temperature is written, and this temperature is Tsat. You will compare your temperature that is given in the question with this Tsat. If it is greater, then it is superheated. So this is the idea. And then if it is less, then it is subcooled. If it is equal, then it is saturated. But if it is saturated, I cannot define whether it's saturated liquid or saturated vapor or saturated mixture. Unless they told me in the question that, for example, quality is equal to that much, then I would be able to know. يعني, if the quality is between 0 and 1, then it's saturated mixture. But if the quality is 0, then I know it can be saturated liquid or it can be compressed, because even the compressed has no vapor. خلاص? But if X is equal to 1, then it's saturated vapor. You can see? Now here how you think and try to understand what's going on. Then, let me just make sure that nobody raised any question. Yeah, okay. And as Ali mentioned, yes, it is superheated, as I said. So you will notice that it is superheated and you will get the S value. Okay, the S value, I think you will get it as 6.8148 kilojoule per kilogram Kelvin. Okay, that is with regard to state number 1. With regard to state number 2, again, you would have to do the same. At state number 2, you have T1, which is equal to T2, so it's still 200 degrees C. But at P2, here where you are going to go to table F2. And you will also notice that the temperature is greater than Tsat that's given. And if this is the case, you go to the table and find at this temperature how much is this. Okay, and you will get the S as 7.6439 kilojoule per kilogram. So look, by having S1 and S2, I can easily calculate the Q. So Q reversible supposed to be equal to 473.15 multiplied by delta S value, which we have them now here, 7.6439 minus 6.8148. Okay, so with that I can find the amount of entropy. It's 392.29 kilojoule. Now, according to what's given in the question, they already give me that the mass is 1 kilogram. But so I can just write it here as kilojoule per kilogram. And to get it as kilojoule, then you will multiply it by 1 kilogram. Okay. And this is just the end of part A. And this is what they need in part A. But I can modify part A by asking, for example, how much is the work as well. Of course, if they ask for the work, then you would have to substitute in the first law of thermodynamics. And I already explained that once you get to Q, you can just substitute in this equation to find W, because delta U can be easily found using the same approach that I mentioned here on the left side. Okay, so that will end part A. Now, with regard to part B, I guess from now onward, I will not go and put numbers. I just need to cover the whole ideas that are given in the other question, just to save time. Because apparently we don't have, I think we only have like 15 minutes or so. Then, with part B, what they said the path is different here. They said, no, it undergoes reversible adiabatic expansion. It's no longer isothermal, it's adiabatic, but at the same temperature and pressure given initially and same final pressure. So P2 is the same, T1 and P1 is the same, but the path here, instead of being reversible isothermal, now it's reversible adiabatic. And I guess you all know what reversible adiabatic means. By now, reversible adiabatic would have a very important meaning, which is delta S is equal to 0. In other words, the link here in this part between state 1 and state 2 is not the temperature. The link is what? Is entropy. So what you are going to do at step number 1 is that you are going to find S1 at T1 and P1. From where? From table F2. Then at state number 2, you will say at P2 and S2, which is equal to S1, so you have two properties here, you will be able to define the state and find out whatever information you need. And in the question, what they need in terms of information, they say it's reversible adiabatic expansion to the final pressure of 150, same as before, but they were asking for two things. One is the final temperature. The other one is how much work. All right. Now, again, I would say, since I do have from step number 1, I found at T1 and P1, I find S1. Okay, from step number 2, that I'll just call it step number 2, at P2 and S2, you have to go and figure out how much is the temperature. How is this? Because you will notice at P2 and S2, you will go in table, the procedures will be as follows. Using table F2, go to P2 equal to 150 kilopascal, and then horizontally at 150 kilopascal, horizontally, you do have the first column which shows two things. What are those two things? The S property. Here I have S liquid, here I have S vapor. So what I want to do is just to compare my S, which is S2 here, check S2, is it greater, less than, or equal to the values we have? And in this question, let me just double check what is the phase. Okay, in this question, you will notice that S, it lies between S liquid and S vapor. If this is the case, then it is saturated mixture, and I will repeat, once you have been told that, once you have discovered that it is saturated mixture, then always should come to your mind X supposed to be calculated. Because if you did not calculate X, you cannot determine any other property. And what is the property we are looking for here? We are looking for the temperature and we are looking for the work. And then if it is saturated mixture, Doctora, we have no problem. لأن if it is saturated mixture, then the temperature is simply Tsat. Totally agree. And with the temperature, you have no problem. Why no problem? Because at 150 kilopascal, table F2, you will go below the pressure. There is a value here written, and that value is Tsat. Khalas, I can answer this question. T2 is equal to Tsat. I have no problem. But if they ask for other properties, it is saturated, but is it saturated liquid, saturated mixture, or saturated vapor? It is saturated mixture. Then if it is saturated mixture, then I cannot take M liquid as a value for any property they ask for. I cannot take M vapor as a value for any property they ask for, but I have to find the quality that will allow me to calculate the exact property they need. And the question is, what is the property I need? Why, Doctor, you are calculating X? Okay, I calculate X because I want to define the system. But to know what is the property I need, let me just go back to the question and see what they need. They need W. And from part A, we said to find W, we have to substitute in the first law of thermodynamics. It's a closed system here, according to what's given in the question. And it's adiabatic, then this is equal to 0. In other words, to find W without calculating delta U, I won't be able to solve. So here is the idea. The idea is how to get delta U. طبعا, at P1 and T1, we already said from part A that U1 can be calculated. Khalas, I explained that. But to find U2, I do have P2, which is equal to 150 kilopascal, but I need to know how much is the quality to solve. الحين, what is the link between initial and final condition? We said it is the entropy. يعني, if I substitute it in this equation, S2 is equal to S liquid plus the quality into SLV, or SV minus S liquid, then I should be able to get the quality. How to get this? طبعا S2, it is same as S1, and to get S1, we already found it from part A again. So S1 you have it. S liquid and S vapor, you will get them at a pressure 2 equal to 150 kilopascal, as I mentioned here. Okay, in that sketch, the purple sketch. And in this case, you have S liquid, you have S vapor, then find the quality, X. Then, that is, I would call it here step number 3. Step number 4, I found the quality, then easy to find U2. U2 is equal to U liquid plus X, U vapor minus U liquid. And just direct substitution, you can get U2. خلاص, step number 5, then substitute, just leave this one up. Okay, substitute in equation in step number 3. And this will allow you to get W. خلاص? So this is the procedure. You have to make sure that you can substitute and solve. طبعا, based on whatever I did so far, the work is going to be only in what? In kilojoule per kilogram. Of course, to find it in kilojoule, then keep in mind that the mass was given, then you will multiply it by the mass, because the mass is given in the question. Okay, so that basically the second problem, which is problem 636. All right. Okay, so we'll move to 637 here, and again I will elaborate on the idea. With 637, again it's direct, straightforward if you know how to use the thermodynamic tables. What we have again, we have a steam, the initial pressure is given. Now keep in mind, when they say 6% moisture, moisture means what? Means it is the amount of liquid in the system. This is moisture. So because of that here, this is not the quality, but this is the mass fraction of liquid. يعني 0.96 is actually the quality. يعني 96% is amount of vapor. يعني X is equal to 0.96. Be careful so that you don't make a mistake in the future. So state number 1, it's well defined, because state number 1, I know it is saturated mixture because the quality is given and the pressure is given, and that's enough for me. Saturated mixture with a given quality. So that's enough for me, because once I know the quality based on the previous example, we can define any property. We can get it from the thermodynamic table and substitute to get the exact value. And with the final state, they said it is heated at constant pressure. So here I have constant pressure process. It is heating, and this gives same pressure, 2000 kilopascal, because it's constant pressure. P2 is equal to P1, but the temperature is given as 575 degrees. What they ask for here, they ask for the amount of heat per kilogram, yani in kilojoule per kilogram. How much is the amount of heat? To solve this question, now I don't know whether it's a closed system or open system, but regardless, as long as the pressure is constant, then definitely Q is going to be equal to delta H, and you all know that. If it is a closed system, okay, if it's a closed system, then and constant pressure, then Q is equal to delta H. And if it is open system, again Q is equal to delta H. So in other words, to find Q, I have to know how much delta H. So for state number 1, again we said it is fully defined. Fully defined means what you are going to do here, you are going to go at pressure P1 is equal to 2000 kilopascal. It is saturated mixture. So you can go to table F1 or table F2, but because it's a pressure based, maybe easier to go to table F2, find the value of H liquid, find the value of H vapor. How is this? When you go to the table, you choose the pressure, which is 2000, and then the first 2 columns in the table, you will get the liquid property and vapor properties, as I said before. So those 2 values will represent, here you can get H liquid and H vapor. So once you are done with this, you can just substitute, get H1 is equal to H liquid plus the quality which you have it, H vapor minus H liquid. So it's done, and you can get H1. That's with regard to state number 1. So this define H at state 1. Okay, to get H at state 2, again, I have both properties. What I advise you to do, here you have 575 degrees C. Probably if you can get this from table F1, fine, otherwise go to table F2. And then here I would just go to say at state 2. Okay, P2 is equal to 2000. Try to see whether it is superheated or saturated and find the value. Okay, so then the idea is simply Q is going to be equal to. Okay, let me just. It's not accepting. Yeah. Okay, so let me just double check the states. So just to make sure that you will not get struggled. Okay, yeah, okay, good. So actually here you will find it as superheated. So if it is superheated means you will notice that at P2, the temperature that you have, which is 575, is greater than, just go upward. Okay, the temperature that we have in this question is greater than Tsat. And because it's greater than Tsat at this pressure, then it is superheated. Okay, and if this is the case, خلاص, all you have to do is just to substitute in the Q equation, which is equal to delta H, يعني H2 minus H1, which we found based on the given procedure. So that is basically this question. It's very simple, but you need to combine between whatever we studied in this question, in this chapter, and what we covered in the previous chapters. Okay, last thing, in the last 5 minutes, I want to cover 638. 638 is quite useful as well because it combines several or more than one chapter. So let's see what we have. Here we have a steam at a given pressure. This is P1. The quality is given. So it's similar to the previous question that the initial condition is saturated mixture, but it undergoes reversible adiabatic expansion. So my process is simply PV or the PV diagram. It's reversible adiabatic. In other words, it is what? It is asentropic. يعني delta S is equal to 0. Of course, according to what's given in the question, T1 and P1 are given. So, well, actually, sorry, P1 is given. But it's not only P1 is given, but also the state is defined. They told me it is saturated mixture, and they give me the quality. So in this case, I can find n property. We have no doubt here. But they said here that it undergoes, it is non-flow process, non-flow. So that is very important and useful information because I can apply the first law of thermodynamics for a closed system. It's not a flowing system. The final condition here for the pressure, as given in the question, it is 400 kilopascal. Now, the beauty of this question is that it combines two paths process. They said it undergoes reversible adiabatic expansion and then followed by another path, and this path is what? Heating at constant volume. So in other words, I do need to have another path here, which is heating at constant volume. So if this is my state number 1, here's state number 2, and there is state number 3. Okay, so you can see several ideas we are giving here, several questions, but state number 3 is defined as saturated vapor. Okay, and here is the most important thing. So what they ask for Q and W for the whole process. Okay, I will make a summary for you here on what we have. If I will start with, I have actually three states, state 1, state 2, and state 3, right? What I will do here for you, I want to discuss with you how can we get the paths, okay? We have the path 1 to 2, and through 1 to 2, it is reversible adiabatic. So if it's reversible adiabatic, you know that Q is equal to 0, and you know that W is going to be equal to delta U. That's wonderful by its own, right? With the path 2 to 3, because they ask for Q and W, so I'm trying to find Q and W in each path. For 2 to 3, it's constant volume, so W will be equal to 0, and because it's constant volume, so in this case, Q is the one that's going to be equal to delta U. خلاص? So if I call this one Q12, W12, this is going to be Q23 and W23. Okay. In the question, they did not ask for each individual. They were asking for Q and W for the process. So what I have here, delta U for the first path is simply U2 minus U1, but W for the second path is U3 minus U2. And if I want to find for the overall, okay, for the overall, to find the Q total, you can see one of them is 0, the other one is delta U. So Q total is simply U3 minus U2. While W total is the summation of those two for both paths, and it is equal to U2 minus U1. Okay, in other words, I know that what I need to calculate in all this is the U values. Once I have U1, U2, U3, then I can solve. So this is the idea, how to get U1, U2, and U3. Step number 1. At state 1, do you have any problem finding U1? Of course not, because at state 1, you do have P1, you do have X, which is equal to 0.9. Then to find U, it is simply U liquid plus X ULV. And whether you use table F2 or table F1, you should be fine. But because the pressure is 700 kilopascal, I would prefer if you can find it in F2, just go ahead. And the first two columns will show you the liquid properties and vapor properties, and then you can substitute. So I have no problem finding U1. Okay, number 2, I need to find U2. So at state 2, how can I find U2? Somebody will say, Doctora, we don't know anything other than P2. Here is the point. Try to find the link between P2 or between state 2 and state 1. It's a reversible adiabatic, it's asentropic, then delta S is equal to 0. So S2 is equal to S1. Okay, and in this case, at P2 and S2, you can fully define the system. And because you can fully define the system, you can find U2. That's it, full stop. I will not go into the details of how to get it, because based on its property, if it is superheated, you will get it from table F2. If it is saturated, you will get it from table F2, but the first two columns. Khalas, full stop. Number 3, state number 3. Now, state number 3, again, when you go to the figure, state number 3, you only know that it is saturated vapor. Okay. It is saturated vapor, but I don't have any information. I have so many saturated vapor information, but again, you will have to go and see the link. What is the link between 3 and 2? It is constant volume. In other words, you have to go to property at state 2 and find V2, specific volume. And here you will find U2 and you will find V2 as well. So at state number 3, V2 is equal to V3. And in this case, at saturated vapor, according to what's given, it's saturated vapor, and V3 is given. What you have to do, you have to go to the vapor property, whether it is in table F2 or F1. Find out this V3 is where on that. Once you get it, try to see the corresponding U accordingly. So once you are done with that, in this case, you were able to find U1, U2, and U3 in this example. Then you have just to substitute in those above equation. I'm sorry that I was just illustrating the idea behind it. Now it's your duty, especially with this question, your duty to practice how to get those information and to substitute here. So as a conclusion, I was trying to cover the most important problems, and I think from my experience, if you know how to solve all those problems, then you are okay with this chapter. That is from my experience. So today morning we covered 2 problems, which are 625 and 628, if I'm not mistaken. And now I'm covering 630, 636, 637, and 638. Before I leave and end the lecture, anybody has any question? Anybody has any question? Yeah, fine. Mina is okay with it. About the rest? About the rest? Okay, great. If this is the case, I would have to announce the end of this lecture, and we'll see you on Thursday.